Hello, algebra students. Mr. Lawrence here, and this is one of my most favorite things to work with in algebra because we start to see how these quadratics have applications in the real world. Yeah, we're going to be doing some story problems for the next few days, and they're very, very simple. I got to tell you, I was very proud of the way most of you handled the story problems from the mixture section. You're showing a lot of maturity, and if I would have tried to do something like that with you back in September, October, a vast majority of you wouldn't even have tried, and you would have given up, and you would have said it was too hard, and you would have blamed me or the flip model, and I would have got ugly letters from parents. But you guys are being so much more mature. You're growing up, and you're realizing that you hold the key to your success. If I'm just an average teacher, but you're doing your best, you're going to learn a lot no matter what. So I'm very proud of you for those efforts. Keep that going. All right, so we've had this equation. A lot of you get really intimidated by equations. You don't need to. Let me point out to you what everything is here. Okay, this means it's a function. We see like h of t or f of x, right? You've seen those before, that functional notation. This is the height after t seconds, after a certain amount of time. Okay, and this is done in seconds. We could do a different time, but this equation is set up for seconds. All right, this 16 is, it comes from the gravitational pull of the Earth, and we're dealing in feet per second here. If we were dealing in meters per second, it'd be negative 9.8 sitting there. Okay, but it has to do with the gravitational pull of the Earth on a different planet or on the moon or something like that. This would not be the right number, but on Earth, it is. Okay, now, it's not just made up, it's done through observation and calculations and things called calculus. We're not going to go into the derivation of this. It's been too long. I probably couldn't tell you exactly where it comes from, but I can tell you that it does come that everything on the Earth falls at 32 feet per second squared in a vacuum. Okay, it's neglecting air resistance. All right, t is obviously time. T is time again here. That's the time squared. That's normal time. V sub o just means initial velocity. Initial velocity. Okay, you might want to call it speed, starting speed. Yeah, it is the starting speed. Now, the velocity indicates direction as well. And if something's being fired up, it's going to be a positive. And if it's fired downward, it's going to be a negative velocity. Okay, but the negative only indicates direction. And h sub o is your original height, or initial height, or your starting height. So I guess I'll put initial so I can be consistent. Initial height, okay, or your starting height. That's what the little sub o means. It's where you're starting. Let's see how we do a problem now. Number one, a ball is kicked off the ground with an initial velocity of 20 feet per second. So there's my initial velocity right there. That's v sub o. Okay. Hey, it's kicked off the ground. What's my starting height? Oh, my starting height? That must be 0, right? Because it's being kicked off the ground. When will the ball come back to the ground? So my ending height, h of t, is going to equal 0. Not h of 0. Notice I didn't put the 0 inside. I don't know what t is. So I'm going to set this equation up. I'm going to go h of t. It's going to equal negative 16 t squared. It's going to be plus 20 t, and then plus h of 0. I guess I should have put v sub o t there. All right, so now I know this is 0 because I'm wondering when it's going to hit the ground, right? Right there. Okay, negative 16. I don't know the time. That's what I'm trying to figure out. The initial velocity is 20 feet per second. I don't know the time. And this is 0. Okay. I could go a couple different routes on this one. I could go with the quadratic formula to solve this, or I could factor it. I think on this particular one, I'm going to look to factor it. Maybe I'll do it both ways since you're such a new learner at this. All right. So I'm going to take the negative 16 t squared plus 20 t, and of course equals 0. And I'm going to factor out the GCF. I'm going to pull a, I think I'll pull a negative out. I'll pull out a negative 4t. I'll be left with 4t minus 5, right? Remember factoring by GCF? Now I've got two things. I've got this factor, set it equal to 0. Negative 4t equals 0. Divide by negative 4. So t equals 0. Okay. T equals 0. Well, that's the starting time. So that's not what I want. I mean, that's when it's on the ground to begin with, right? Now I'm going to solve 4t minus 5 for 0. Adding 5 to both sides. And I'm going to get 4t equals 5. Divide by 4. Divide by 4. The time will take 1 1/4 seconds. Yeah, it's pretty amazing. It'll take 1 1/4 seconds if I kick it off the ground with an initial velocity of 20 feet per second. Now, of course, when I do this, the ball is going to take a parabolic path, right? And that's why this works. So it's going to go like that. And obviously, that's not a very strong kick, 20 feet per second. Okay, now, let me show you how to do this with the quadratic formula, because there's some situations where factoring won't be practical. Okay, so let me get rid of this. So here's my A, B, and C, right? A, B, C. Easy as negative 16, 20, 0. All right, so I'm going to go with x equals the negative of b plus or minus the square root of negative 16 squared minus 4ac all over 2a. And this works out pretty easy. Negative 20 plus or minus 16, right? Because this is going to turn to 0. Negative 16 squared is 256. When I take the square root, I'm going to get 16. Okay, and so then I'm going to have negative 32. Uh-oh, something's bothering me here. Do I have a mistake? Hold on one second. Yep, I sure do. I have a silly mistake. This here should not be a negative 16 in there. It should be a negative 20. Glad I caught that, because that would prove to be difficult. So let me change that. It'll be a positive 20 in there. Okay. That, of course, will change this to 20, and I like that a lot better. So negative 20 plus 20 is 0 over negative 32, which simplifies to 0, which is what I got the first time. And then when I do negative 20 minus 20 over negative 32, I'm going to get a negative 40 or negative 32. The negatives will cancel. I'm going to divide them both by 8, and I'm going to get 5/4, which is 1 1/4. So there you see it works out the same way. I wouldn't have done this one by quadratic formula, but I did it just for your comfort level. Okay. Now this time we have a rock that is being dropped off a cliff. Now, the way this problem is written, you know, some of you are going to think that, oh, okay, this is my rock here. You know, the cliff is 100 feet. Well, we're assuming that the rock is being dropped a distance of 100 feet. Okay, how long will it take for the ball to hit the ground? Well, I still have the same equation. H of t equals negative 16 t squared plus or minus v sub o t plus h sub o. All right, well, let's see. 100 feet tall. To me, that's the top of the cliff. That's the starting height. So that's h sub o. Okay, it's being dropped, right? It's being dropped. It's not being thrown down. So v sub o, the original velocity, is 0. There is no starting velocity. And I want it to hit the ground. So again, this is h of t equals 0. And remember, we want our quadratics to always equal 0, right? So that's a good thing. Okay, if it didn't equal 0, I'd have to subtract it off. But anyway, so I'm going to get 0 equals negative 16 t squared plus 0t plus 100. So if I go quadratic formula on this one, A, B, C, A is negative 16, B is 0, C is 100. And I go quadratic formula, x equals negative of b plus or minus square root of 0 minus 4 a c all over negative 16. So 0 plus or minus. Okay, now I'm thinking, these numbers are all perfect squares here. I'm thinking that one is going to be positive, so that's a good thing. But I have 4 times 16 times 100. Remember when we simplified rads? Let's work smart, not hard. This is 2 times 2. So there's a date, right? Okay. This is 4 times 4. There's another date. And this is 10 times 10. So when I'm doing the square root of this product, I don't want to multiply it all and then take the square root of it. Now sometimes I'll have to, it won't be pretty, but this is an easy one. I'm going to have a 2 out front, a 4 out front, and a 10 out front, and that's going to be 80. I believe the square root of that number will be 80. I could know if I'm right by multiplying them together, and I'll bet I get 6,400. I'll leave that for you to verify. So this square root is going to turn out to be 80. And that's going to be over negative 32. Okay, so the negative answer isn't going to do me any good. I'm going to ignore it. 80 divided by negative 32. It doesn't make any sense. I'm not going backwards in time. So my t, and I used x there, but I guess technically it would be t in this problem. It's going to be negative 80 over negative 32, because the two negatives will cancel each other out. And then I can do 80 divided by 32. So let's see here. 80 divided by 32, and we're going to get about 2.5 seconds. It'll take 2.5 seconds for this ball to fall. That's a nice, pretty answer. Usually they end up pretty uglier than that. I must have picked some good numbers. All right, now by the way, I've got another way to solve this one too, because when you understand math, other opportunities open up to you. You don't have to be a slave to doing something one way. You see this equation? I know that 16 and 100 are both perfect squares. Watch what I'm going to do. I'm going to rewrite it as like that. I'm going to subtract 100. Negative 100 equals negative 16 t squared. Divide by negative 16. Okay, and so I'll have t squared, which will equal 100 over 16. But then I'm going to take the square root of both sides to undo this square. Take the square root of both. And this is really cool. The square root of 100 over 16 is the same as the square root of 100 over the square root of 16, which is the same as 10 over 4, which equals 2.5. And there you go. So it takes 2.5 seconds for this ball to fall. So you can use the quadratic formula, but there are other, sometimes easier ways to work on it. All right, let's do one more problem. A rocket is launched off a platform that is 25 feet off the ground. So here's my platform. It's 25. Let me draw my rocket. There we go. There's my rocket. Don't like it? Tough. Take it up with Mrs. Wenmouth. I'm sure she can show you how to draw a rocket better than that. All right. Now I know it's going to be launched off the ground. And the second it gets launched off the ground, or off the platform, gravity is going to start pulling on it. And it's going to fall in some type of parabolic path until it hits the ground, right? Okay, so let's go through and see what we have here. A rocket is launched off a platform 25 feet. That's my starting height, 25. Initial velocity is 100 feet per second, and how long it would take for it to hit the ground. So the ending height is 0 again. Okay, and some of you are thinking, oh, the ending height's always 0. Not always. So let's set up my equation. So h of t is going to be 0 equals negative 16t squared plus v sub ot. So this will be negative 16t squared plus 100 t. And the starting height is h sub o. Or the, initial height, right. And so it's plus 25. All right, so here we go. Now, by the way, if you end up with a perfect square trinomial or something like that, this is not one, but if you ended up with one, you could factor this. All right, so I'm going to go A, B, C, easy as negative 16, 125, and so I'm going to go to my quadratic formula. So x equals the negative of b plus or minus the square root of b squared minus 4 times negative 16 AC all over 2a. All right, so we're going to simplify as best we can, get negative 100 plus or minus, let's say 1, 2, 3, 4, plus 4 times 25 would be 100, 400, 1600. Did I do that right? I think so. 25 times 16 should be 400, right? Let me see, 0, 3, 12, 17, 20, carry the 2. Yep, 400. And if I double 400, yeah, 800, 1600. There we go. All right, and that's all over negative 32. So x equals negative 100 plus or minus square root of 11,600, and that'll be divided by negative 32. Okay, so that's getting pretty ugly there. I'm going to go to my graphing calculator on this one. See if I can't let's see here. Get myself set up. All right, so I'm going to have the quantity of negative 100 minus the square root of 11,600. Close that quantity, close the first one, and divide by negative 32. And I get about almost 6.5 seconds. That's pretty cool. Okay, so it's going to be about, so t is going to be approximately 6.49 seconds. So it's going to fly for basically 6.5 seconds, just a little bit shy of that. Okay, now if you're wondering, do I need to go find the other 0? No, I don't. Watch what will happen if I do. Hopefully you already know, but in case you don't, and I'll change that to a positive, and look, I get a negative amount of time. A very small amount of time, but a negative amount of time nonetheless. And let me see here. Let me hide that and make him take a full page. Let me go back to my wonderful picture. You see that parabola there? Okay. That negative amount of time that I got would be this. It would be taking this parabola back to where it started from if it had been launched from the ground. Okay, it hadn't. It's actual, from going nose to nose, right? It'll be from there to there. That's the nose of the rocket impacting. By the way, it's getting deformed, but whatever. You get the right idea. And there's the blue fire coming out the tail. All right, that's it for the video. Pretty cool stuff if you ask me. We'll get some practice with this over the next few days. Mr. Lawrence signing off. Have a good night, everybody.